Well, hello everyone. Welcome to week 2 of the semester. I'm Professor Rios, and this week we move on to a topic that is sort of building block material. FYI, a lot of some of the material in this lesson we will get back to in subsequent lessons. So I introduced some of the material early. It may not necessarily be in the reading yet, but it kind of comes back. So that's kind of the whole point of doing that. So otherwise, be aware of all your deadlines for the week. Make sure you go to the to-do list and see everything that's due. Don't forget Google Earth. You hopefully already took care of downloading it for week 1 and also watching the video that explains sort of a little bit of a, not really a tutorial, but kind of a brief demo on Google Earth. It gets used throughout the semester, so and I tend to give those homeworks a little bit more point value emphasis. So please bear that in mind. All right, so let's get going. So week 2, Earth-Sun relationships, so seasons, radiation, and the heat balance. So we talked about how Earth is a system, and this system is super complicated, quite frankly, and we live in it. So let's talk about some of those relationships and some of those concepts now. So these are the objectives. So, what is the reason? Why do we have seasons? Why is it so different in June here in New York than it is in December? What's the point of that? Why does that happen? So we'll talk about that. The idea of prominent controls of temperature and all kinds of other good stuff. So these are the 5 main objectives for week 2 lesson. All this stuff affects atmospheric and oceanic processes. This image here is of a major Category 5 hurricane over the Atlantic, taken from space many, many years ago. But what I want you to get out of this image is the fact that this big heat engine that is a hurricane is driven by these sort of radiation concepts. So if you think about the Earth orbit around the sun, it is not really circular. It is more of an ellipse, with the sun being off-center. And the Earth is closer to the sun in January. That's called perihelion. And it is farther from the sun on July 4. That's called aphelion. And so that's mainly because the Earth orbit around the sun is not a perfect circle. Okay? So now, look at Earth rotation. It's in an easterly direction, counterclockwise. And because of that, the atmosphere, which is this envelope over it, rotates with it as well. The Earth is tilted about the sun at an angle of 23.5 degrees from the vertical. And that axis is oriented on the North Star. And so that's the basic idea behind seasons as we get going. So there are environmental effects of rotation, and the most obvious one is the diurnal rhythms that you expect. It is generally cooler in the morning, warmer in the afternoon, daylight, flow of air, all that stuff generally has a rhythm. Clearly, temperature can change throughout the day, and it's dependent on whatever weather system happens to be over you, but it is one of the effects that is controlled by rotation. Consistent flow patterns of air and water, so storms in the North Atlantic, or in the northern hemisphere rather, spin counterclockwise, whereas in the southern hemisphere they spin the other way. We'll get into that. And of course, the tides, the ebb and flow of tides, the low and the high tide is really driven by this as well. So there are 3 main environmental effects of rotation that we all experience, really regardless of area of the world. If you look at the Earth-Sun relationship in a little bit more detail, again, if you look at the sun, what is called the plane of the ecliptic is literally cutting the sun in half which literally cuts the Earth in half. Okay, so now during June, the northern hemisphere is tilted toward the sun, whereas in December, that same tilt hasn't really changed. That would be this line here. Notice the line there. And now the northern hemisphere is tilted away from the sun. So this is why in December, the sun sets around 4:30, whereas in June, the sun sets around 8:40. So it makes a big, big difference in the amount of sunlight. And as a result, it makes a big difference in temperature. Again, if you look at it from the perspective of sunlight and sun's rays, the sun rays are very, very, very perpendicular to the surface of the planet on June. But if you go into the northern hemisphere, that is when the entirety of the Arctic region is illuminated, whereas the southern area is not illuminated. And then if you switch to the next image here, December 22nd, our winter, the southern hemisphere summer, now the southern hemisphere is illuminated, whereas the northern hemisphere is not. Okay, and now if you're near the equator, so right around the center of the Earth, right in the middle, it doesn't really change that much from season to season. The difference is almost unnoticeable. Okay, whereas you can notice in December and June here in New York, the difference in sunlight. If you go to a place like the equator, the sun may rise at 6:10 in 1 month, and then in the opposite time of the year, it may rise 8 or 9 minutes later or sooner. So the difference is not really noticeable. Here is looking sort of down. If you were looking literally above the sun, and you have the Earth, and you could sort of magnify, obviously this is exaggerated, but here in June, the entire Arctic Circle is illuminated, whereas in December, it is not. In March, it is sort of halfway and halfway. So as we go from December or winter in our hemisphere to March, spring, June, summer, summer, back to fall in September. So that's the sort of, that controls the seasons, which of course controls the amount of heat. Okay. You know, in the northern hemisphere, high latitudes where you're above. So if, for example, you're above the Arctic Circle, somewhere in here, you tend to have this, the sun never setting. And there are a few videos for you to watch on the YouTube channel that sort of highlight this in a form of video. So it's easier to sort of grasp the fact that the sun never sets. And here's an example of June. At latitude 90, there's 24 hours of sunlight. Latitude 80, latitude 70. But if you go all the way to the southern hemisphere at latitude 70, 80, or 90 south, there is basically no sunlight. The sun never pokes above the horizon. This image here is a little bit complicated, but not really that difficult. These are the months, January, February, March, all the way through summer. And this is giving you a amount of energy, okay? So notice if you're at the equator, notice how little the color changes. Orange, 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 right? There's no change. If you're at the higher latitudes, you go from no energy to a lot of energy to no energy. So the change is really dramatic across the months of the year. We're at latitude 41, so we do have a significant change in radiation. But if you're at the southern hemisphere, notice how it's opposite. It's during their winter, which is July and June and August, it is little energy, and during their summer, which is January, February, March, you have a lot. So that's just giving you a sense that depending on where you are, you either have a weak seasonal cycle of energy or a very strong seasonal cycle of energy. And that reflects itself in temperature. Here's another another way of looking at that, same latitude on this side, time of year on this side, and these are the number of hours of sunlight. So notice 0 hours all the way to 24 hours. So during their summer, a lot of sunlight, no sunlight, a lot of sunlight. However, if you're near the in between the tropics, notice how the seasonal cycle is frankly rather weak. It doesn't really change that much. So as a result, you tend to have roughly 12 to 14 hours of sunlight anywhere in this bar. Okay. All right, so intensity of radiation with latitude, the higher you are in latitude, so 75, 35, or 0, the higher in latitude you are, the more of the atmosphere that energy has to cross. And as a result, that energy is diffused, like it's stretched out. Imagine grabbing a whole bunch of cotton and just literally pulling it apart. It becomes thinner and thinner and thinner, so it has less effect. So as a result, it doesn't heat up as much. Whereas if you're at the equator and the sun is directly above you, you feel that energy rather intensely. It is really, really intense, where you have to wear long sleeves and hats because you can easily be sunburned. So how do we heat up the atmosphere? We think about the idea of temperature, whether you're measuring in the Fahrenheit, Celsius, or Kelvin scale. There's a freezing point for each and a boiling point for each. And temperature tends to, wherever you are, this happens to be from Saudi Arabia, one particular year, there is an annual temperature range. You have a daily temperature range. You have a high and low for a day, but then you have a high and low for the year. So in Saudi Arabia, this particular year, the high was 132. The low was about 54, 53 degrees. So that is the annual temperature range versus daily temperature range. Solar energy, where we're talking about the idea of electromagnetic energy, the energy that comes from the sun in the form of visible energy, what you see outside, the bright sunlight. You can see that with your eyeballs. There's also other types of energy like ultraviolet and infrared, which are basically invisible to us, but they do have a significant role to play in the heating of the atmosphere. So the sun is most effective at emitting energy in the visible. The earth is, on the other hand, most efficient at emitting energy in the infrared. Okay, and this energy, while important, it's called terrestrial or long wave. We don't see it with our eyes. Whereas what comes from the sun is either called solar energy, makes sense, or short wave. Okay? The shorter the wave, the more energy it has in it. Albedo. Albedo is a pretty important term. It is basically the percentage of sunlight that's reflected by a surface. So think about a bright, sunny morning after a snowstorm. That energy is reflected rather intensely. Okay, that's called albedo. And it's reflecting insolation, which is an acronym for incoming solar radiation. Okay, don't confuse it with insulation, which is what you put in your walls to keep the heat or the cold from coming into your house. So don't confuse it for insulation with a U. Albedo depends, this happens to be two particular years, 2002, a long time ago, but it really doesn't matter. It's still useful. In February, there's a lot more snow and ice up in the northern hemisphere, so our albedo is high. In summer, it is more grass and dirt that's basically here, so the albedo is lower. And you can look at these sort of on your own, but just to give you a sense of what doesn't really change would be deserts. So here's the Sahara Desert or Saudi Arabian desert. It doesn't really matter what time of the year it is, August or February, it is still very reflective because it is made up of bright material, sand, okay? Solar energy has to be thought of as a budget. So the Earth has an atmosphere, and because we have an atmosphere, we have what's called a greenhouse effect. Solar energy comes in, some of it escapes, but some of it is trapped by gases, and those are greenhouse gases called water vapor, carbon dioxide, methane. If the Earth had no atmosphere, the Earth would be a much, 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 much colder place because the energy that would come in would leave during the night. So energy in would equals energy out. Because we do have an atmosphere, some of that energy from the sun is retained. And as a result, we have a planet that is livable. Okay? So some of the basic heating and cooling processes, you've heard of almost all of these, with the exception of probably this last one here. So let's look at them. Conduction is molecule to molecule heat transfer. Think about putting a skillet made of iron on the stove. If you come back to it half hour later, you would not want to touch that handle because that molecule to molecule heat transfer has made the whole thing very, very hot. And here's an example of putting a metal rod into a fire. Hotter, a little cooler, cooler still, cold. Eventually, over time, that heat, molecule to molecule heat transfer will take these, which were here, and heat them up as well. Okay? Convection, heat transfer from one point to another through a vertical circulation of fluid. If you have a home with these sort of heating coils, you are using convection to heat your house. You may have a convection oven to help heat and cook your food. Same basic principle. Okay, a boiling pot of water would be a good example of that. Advection is heating where the dominant heat transfer is in the horizontal. So think about that first warm spell in April or March or May, depending on the year. And where did that warm air come from? Well, it came from the Gulf of Mexico. So it basically got transferred from the Gulf all the way through the United States into the Northeast, warming our environment to a significant degree compared to where it was. That is advection. Okay. Adiabatic cooling and warming. We'll get into this in more detail in an upcoming lesson, but it's definitely worth, in fact, week 3, it's worth highlighting now. As air goes up or down, the temperature will change because of different pressures it experiences as you go up or down. So that's called adiabatic cooling as you go up, or adiabatic warming as you go down. Again, we'll get to this in more detail next week. Latent heat is the one that you're probably least familiar with. And this is the heat that happens that you either gain or you give off when you change state. And by changing state, I mean melting, freezing, condensation, evaporation are the ones that we're going to focus on in this class. So for evaporation, that would be this one here, you require energy from the environment, so the net result is you feel cold. Think about taking a hot shower in the middle of winter. You go into the shower and you're super comfy because it's nice and hot water, but the second you step out, you feel cold. And that's because the water on your skin surface is evaporating and cooling you down. Okay? So putting it all together, these different mechanisms contribute to what's called the atmosphere or greenhouse effect. And because we have an atmosphere made up of water vapor and carbon dioxide and methane, we have a planet that has a livable temperature across its surface. Even if it may be super hot in some areas and really cold in others, generally speaking, averaged out over a long period of time and over a bigger area, it is basically a temperature that is frankly pleasant and livable across. Here's the idea of the atmosphere effect. Think about an actual greenhouse. So what are some of the things that control temperature? So latitude, the further north you are, the colder it gets. The closer to the equator you are, the warmer it is, and the least it varies. Altitude, being close or far away from water, and ocean currents. These are the big ones. So here's an example of prominent controls of temperature. So this is summer in the southern hemisphere, winter in the northern hemisphere. Notice what the temperatures will look like. And then you flip it around and you go summer in the northern hemisphere, winter in the southern hemisphere. Notice how the lines of temperature don't change much compared to, look at their winter and their summer. There's more land in the northern hemisphere than there is in the southern hemisphere. So as a result, the temperature changes are a lot more dramatic. Here's the idea of temperature range. Of course, insolation and latitude. So the further north you are, so this happens to be December. So December is our winter, so there's less insolation here, more down here. And during June, our summer, there's more insolation in the northern latitudes, less in the southern latitudes. Angle of incidence, already talked about this. The further north you are, or the further south you are, the more area that energy has to cross, the more atmosphere. And as a result, that energy tends to be sort of thinned out. Whereas if you live near the equator, the energy goes through a smaller area. Therefore, that punch, it has more punch and therefore can heat more. And again, if you've ever been really close to the equator or in the Caribbean or really, really low latitude, like say the Caribbean, Puerto Rico, Brazil, you know what I'm talking about. The sun feels more intense. Here's the idea of the sun's rays at the equator directly above you, making a 90-degree angle, or at the polar region where it's barely noticeable. Even though the sun may be out, it feels cold. And you know that. Think about a super cold winter day when the sun is out, but it barely feels like it's warming you up. Here's an example of a convection oven, essentially, Death Valley, California. You are heating the valley itself. The air is going up. It's cooling. Notice there's snow in the mountains here. And then that air then sinks again, and you get these sort of convection cells going. Land-water contrast. It's like the difference between living in Coney Island or near Coney Island and living up in the Adirondacks. Up in the Adirondacks, you're far from water. You're in the middle of land, and it gets much, much colder. You know that. If you've ever been to upstate New York in winter, you know how much colder it gets. If you're way up in, like, Tupper Lake and all those sort of like isolated winter resorts up in the Adirondacks or Catskills. Whereas if you are near, say, Jones Beach, Staten Island, the Jersey Shore, it doesn't get that as cold in winter, but it doesn't get as hot in summer either. So water tends to be a regulator of temperature. It takes away the big giant peaks and the giant dips in temperature. And here's an example. Two cities, Dallas, Texas, San Diego, same latitude. Notice how San Diego doesn't get as hot in summer, but it doesn't get as cold in winter. Dallas, for example, can be quite cold. In fact, in 2021, Dallas was basically at below zero, which is pretty unusual, but is ridiculously cold. That would never happen in San Diego, being so close to the water. So ocean currents also have a significant impact. Ocean currents, of course, can be hot or warm, like the Gulf Stream off the east coast of the United States, or they can be cold currents, like what's off the California coast. And here's an example of temperature. So the color should tell you what the temperature is. Notice as you are in the Gulf of Mexico or off the Florida coast, this is warm water. As you head north, the waters cool down significantly. So this is excess energy that's being taken away. Here's the actual Gulf Stream. Notice how it takes water all the way towards Europe. Okay. And this is fuel, eventually fuel for things like hurricanes and tropical cyclones and that kind of stuff. So the point here is that excess heat in the form of warm water is carried by the Gulf along the eastern, I should make that correction, eastern United States on its way north towards Europe. Mechanisms of heat transfer, of course, you have the atmosphere and the ocean. These are the two things that transfer heat. Obviously, there is more ocean, and the ocean affects the atmosphere. The atmosphere can often affect the ocean. So these two are currently constantly affecting one another. Let's see. So heat transfer by water and air currents and weather systems, in the end, this is why we have weather. The Earth is a tilted system that is constantly being differentially heated, meaning some areas get more heat than others. And as a result, we have weather. Weather is a response to this differential heating across its surface. We'll talk about vertical temperature patterns. So the idea of an environmental temperature lapse rate, which is how temperature changes with height. And sometimes normally temperature will decrease with height, but sometimes temperature will increase with height. And when that happens, you get things like this, dust and pollution. So this happens to be Los Angeles, and you can literally see the inversion top. There it is. It's like a lid. And as a result, if you were to measure temperature at the surface and then start going up towards this lid, you would notice that the temperature is literally increasing. So it creates like this lid where air can't escape. And as a result, all the smoke and dust and ash and fires, if there are any, and human pollution from cars and airplanes get stuck. Now, California is a lot better than they used to be at pollution. In fact, days like this are rare now compared to 20, 40, 50 years ago. But this is an example of a vertical inversion. That would be this, where the temperature is increasing with height, creating what's called an inversion. Think about it, inversion. It's inverted from what it should be. Normally, the temperature should decrease with height. So that's it for week 2. Again, we've addressed some issues that we're going to cover again, like adiabatic temperature lapse rates, things like latent heat. So all that will be addressed again during week 3, but I just wanted to sort of introduce it along with some of the other concepts that we've talked about today. Otherwise, I hope you have a great week. If you have any questions, don't forget the live study hour, or you can email me and we can address whatever it is, whatever question you may have. Otherwise, best of luck, and we'll talk to you soon. Bye.